we decided to come to Austin and build this factory. Once this will be done, it will essentially become the first nuclear manufacturing factory of its kind ever built. So we're super excited to be here and to be able to deploy it here in Texas.
For today, I'm back at Aalo Atomics here in Austin, Texas, for another major milestone event. This is their grand unveiling of their factory and also a new major product announcement, and we'll be getting into that in the video. Now, this was opened up to government officials, people within the industry, academia, partners, and the media, and it was really a great opportunity to see what they've been up to. Now, about 6 months ago, if you recall, I visited this site for their grand opening. At that time, it was an opportunity to talk with Matt Lozak and Yasir Arafat, their CTO, about how their systems operate, and I would recommend you take a look at my videos on my YouTube channel. For today, one of the interesting things that I want to go over is some of the changes that have happened specifically with the greater demand of power from data centers and how nuclear energy such as the Aalo Atomic reactor can help. The big news within AI these days is the need for high-powered data centers. But have you heard about nuclear-powered data centers? These centers require a lot of energy. In fact, they could consume up to 12% of the nation's electricity production by 2028. They operate around the clock and they cannot have any kind of disruption in their energy delivery. Now, at Gigatex is just a few miles away from Aalo Atomics. They've been installing the Cortex-1 supercomputer cluster for their AI data center. And to meet the energy demands, they've been doing a lot of infrastructure of increasing the capability of the electrical grid and installing megapacks to ensure that they have that uninterrupted power that they need. Now, what if we powered them with nuclear energy instead? And that is an intriguing idea because nuclear provides 24/7 power. It's reliable, secure, and affordable, can be installed on site, and it will help keep the data centers running day and night. Nuclear power plants rarely shut down, and they are able to operate 18 to 24 months between refueling or even more, saving data centers operators millions in costly downtime. They can use advanced reactors that can be built, as I mentioned, alongside the data centers and scale that electrical need. And that's exactly what Aalo Atomics is trying to do with their Aalo-1 and then Aalo-2 reactors and their Aalo Pods. I was fortunate enough to talk with the CTO and the co-founder of Aalo, Yasir Arafat. He worked at Westinghouse for close to a decade on the AP1000 and the eVinci microreactor program. Subsequently, he joined the Idaho National Laboratories and became the project lead behind the Marble microreactor, which is the first new advanced reactor being built in the U.S. in decades. In fact, they received the 90% design complete seal of approval from the Department of Energy, the first time this was granted since 1977. He's leading the design of the Aalo-1, a 10 megawatt reactor inspired by Marble, and it is what they are building here at Aalo and what we will be talking about today. So awesome opportunity to talk to the man that's helping build this new system.
I think before we talk about design, I want to share a little bit about what the motivation behind the design is.
Okay.
Right? So if we step back towards the problem statement, right? You know, there's a lot of nuclear companies out there trying to develop new designs and whatnot. But I think, you know, when we started Aalo, we wanted to solve the real challenge at hand. If you look at the current nuclear industry, we have a lot of amazing plants that are in operation. Most of those we have built in the 60s and 70s and mid 80s.
And they're very large, too.
Very large. And we've kind of went from generation 1 to generation 2, 3, 3 plus. We haven't gone to Gen 4, which is the advanced reactors. And we've seen 2 plants come up for Gen 3 plus, the AP1000, in Plant Vogel, Unit 3 and 4. Those are great plants, very safe, and you know works well. But the challenge there is, it took us many years, more than a decade, to build those plants. Almost 18 years to build those 2 plants, and obviously that's first of a kind. Once you build a lot of them, it becomes a little faster, but it's still close to a decade to get a 1 gigawatt system. If you look at the data, almost 97% 90+% of the nuclear power plants built around the globe are behind schedule and over cost, over budget. And that's a problem. That's a challenge, because when you think about a project taking longer and more money to build them, it ultimately falls back into the cost of energy it's producing. And that makes the economic case very challenging. Not to mention the billions of dollars you borrow to finance the plants in the first place. So we started to take a step back and say, how do we really solve that challenge, right? And so we are focusing on a 10 megawatt electric, very compact, extremely safe, and factory manufactured reactor. But the fundamental technology, as you mentioned, is the one that is being derived from the Marvel microreactor, which is a program that I started in Idaho National Laboratory. We went through the whole cycle very quickly in terms of development. It is not a brand new technology out there. It is based upon fuel that has been qualified for other reactor types. It's based on steel that we can purchase today. It's based on coolant that we built a lot of reactors in the past. We just combined a lot of these proven technologies to come up with a product that makes a good techno-economic sense. 15 kilowatt electric.
And the Marvel uses a Stirling engine, but you've changed that. We're going to get to that.
Yeah, and so we changed a bunch of things from Marvel. Marvel's a small scale, low powered system. We're trying to push the boundaries as to like how much power we can get out of it. Because at the end of the day, what you're paying for is, dollars, how much dollars you pay per how much megawatt you generate for how long, right? That's what we all pay for. So we have to really bump up that power level. One of the main deltas between the Marvel and the Aalo-1 design is that Marvel heat removal is done by natural convection. Meaning you have a heat source, you have a heat sink, and you've got a gap in between, and once those two are activated, you'll see fluid flowing naturally and you can remove certain amount of heat. We use this method for boiling water on our stoves and chimneys and whatnot. So it's able to remove heat, but not as much, right? So it's limited from that perspective. Whereas in the Aalo-1 design, we're actually we have 3 extremely high flow rate pumped system. So you're rapidly pushing liquid sodium, which is our main coolant, to remove the heat from the reactor. And so when you generate a lot of heat and you're able to remove them fast, then you've got a high functioning, high safe system, right? You don't want to end up in a scenario where you're generating a lot of heat, but you have no means to remove them.
That also lets the nuclear reactor itself run at a higher energy state, is that correct?
That's correct.
And that's actually beneficial for a couple of reasons, right?
100%, and that's the strength of nuclear, is that you have a power source that is self-contained, but also extremely energy dense. And you want to make sure that you can maximize that performance to get the higher energy density. So that's one big difference, pump system. Second is how you control the reactor, right? In Marvel, we've got 4 external, we call them control drums. And those are rotating cylinders where you have neutron absorber and reflector, and you turn these drums around. If you have the absorbers facing the reactor core, then it eats up a lot of the neutrons that otherwise would be used for fission. It will kill the chain reaction, and you've got a shutdown state. You can also use it to control down the power. Whereas for us, we go with a more traditional method where we're inserting neutron poison rods inside the fuel assembly. The reason we took this made this change is to allow us to scale up in the future into larger reactors. When we get really good at building the small one first and making hundreds of them in a factory and be able to bring down cost, we want to take on those learnings and build a 100 megawatt electric system in the future from a single reactor system, right? So it's a much more scalable technology choice. Whereas a control drum, once you go from the Marvel size to even Aalo-1, they become less and less effective. And let alone going even larger, they will become not the best choice to control your reactivity. That's another choice. Third one, as you already mentioned, the Stirling engines. We used 4 Stirling engines, 5 kilowatt each. At slightly lower temperature, you might get 15 to 16 kilowatt. At max temperature, about 20 kilowatt in total. But they don't scale up either, right? That's a technology that's been around for 200 years, but we didn't find an effective way of scaling it up to the point where we can have multi-megawatts generated. So we're transitioning to the good old superheated steam turbines.
Okay.
There are multiple manufacturers that can make those today, and we can purchase them from those suppliers, and they've got a service side of the business to make sure they can be maintained. And the cost of acquiring those systems to plug into our reactor is reasonable. So it's a mature supply chain. Cost is lower relatively compared to something exotic. So we're sticking with the good old superheated steam turbine.
Okay. Not only are you making it small, but you're making it modular. So you could, if I got 2 or 3 of them, I can kind of hook them together, and I could have 20 or 30 megawatts.
So that's our goal. Is we wanted to design a product that can go after a large variety of customers. Everybody starting from 10 megawatt all the way to a gigawatt scale. And the way we envision that is first by daisy chaining multiple reactors to a single turbine.
Okay.
So we can do a 3-pack 30 megawatt, 5-pack 50 megawatt, or a 10-pack as a 100 megawatt system, and then we would then scale up and have multiples of these to get to 200, 300, 500 megawatt or a gigawatt level, right? And so if you kind of step back and think about the scaling model that we're pursuing here, if you go with a traditional route, you would need to get a single gigawatt, you would need to spend 10 years to get there, to get to a single plant. Whereas we're trying to then now build 95% of what goes in a particular plant in this factory, and we're planning to scale up to the point where we can make 100 reactors a year. So that's a 10x improvement with the current reactor industry in terms of deployment and scalability. So every year we can potentially generate 1 gigawatt worth of reactors from this factory. And if you need more energy, you build more factories to scale up from there. So you're repeating the same workforce, the same processes, the same quality assurance program. So not only are you able to build these reactors faster, but you're able to improve significantly on quality, cost by improving the process, and being able to centralize a lot of these activities that otherwise would have happened from site A to site B to site C, where you lose a lot of that learning from one project to another. And we've seen that. If you look at China, in the US we built 3 nuclear power plants. We completed 3 new construction of power plants in the last 20 years or so, and China built in the same time frame 39 of them.
Right.
So that's, you would expect, like, okay, they took a particular design and built over and over again, you would see that learning curve. But if you look through a zooming lens for a particular design, no matter how many they built, the cost doesn't go down significantly. And that's because in a gigawatt scale plant, you're doing a traditional on-site construction where you're not implementing a lot of innovation. You're doing the same rebar, the same method of concrete pour. You're not a whole lot of improvements in your processes. The same workforce doing the work are not translated from site A to site B.
Right.
You're hiring new people to do the same job.
Yeah, well, people who watch my channel looking at Giga Texas, what's going over at Bastrop with the Starlink facility, the Boring Company, down at Starbase, it's all the same thing. It's
same story.
Construction, same kind of look, but you don't get those economies of, well, we built one up here and it's going to be much cheaper.
Right.
So, and another thing that I think is pretty cool about what you're doing is, we think we need energy for electric cars or just to power our homes and all that, but looking to the future, things like AI and having big data centers are going to be super power hungry, and they're going to be looking at all kinds of different ways of powering those systems, and this is one of the ways that they might be able to turn to.
100%, and in fact, we're seeing so much activities in this space where, a lot of the hyperscalers are power hungry. They're desperate for new electricity to fuel their growth right now. And just recently you've seen like 3 Mile Island getting restarted with Microsoft. That's a great demand signal, in a plan that has so much historical context to, essentially turning down a lot of the nuclear work in this country. There's a lot of like historical significance there. And so I feel like, while some folks initially might think like, oh, if I have a gigawatt need for a data center, I'd go build a gigawatt scale plant and not these like mini ones. But if you look deeply, closely into the model of deployment, then the speed of deployments on the smaller ones to get that same gigawatt level power is 10x faster.
Right. Well, again, people who follow Giga Texas down at the south end, they're putting in Cortex, which is the new supercomputer cluster that's going to be doing training for their full self-driving and also the Optimus robot. And once they get that center completely up and running, sometime at the end of next year, they need 500 megabots just for that one center. So and the whole region around here, ERCOT and LCRA are they're actually doing a lot of upgrades to the Sand Hill Energy Plant and putting in natural gas pipelines and doing a whole lot of other infrastructure upgrades just to support the data center at Giga Texas.
Wow, that's amazing. And if you look at Texas as a state, right? I mean, it's just, we traditionally know there's a lot of like oil and gas presence here, but it is really the capital of energy, right? If you look at, wind deployments, we've got one of the largest wind deployment in the country in Texas, even like in solar deployments, right? In just this year, it's going to become, 50% of all the new solar additions going to be done in Texas. So it's not just an oil and gas state, it's a state where we see like this massive innovations and, that's a front runner in new energy deployments. We've done that for oil, for gas, for solar, for wind. I think the next stage organically is nuclear, and hence we decided to come to Austin and build this factory. Once this will be done, it will essentially become the first nuclear manufacturing factory of its kind ever built. So we're super excited to be here and to be able to deploy it here in Texas.
That was a great discussion that I had with Yasir 6 months ago about their plans. Today at this industry, government, and media event, we get a chance to see their updates and their progress. And as you can see, a lot of great dignitaries were in the audience. So let's talk to Yasir and see how he's feeling now 6 months later.
Okay, I'm with Yasir Arafat. He's the CTO and co-founder of Aalo, and last time we were here, we talked about how the reactor itself works, and I appreciate all that great information.
Absolutely.
But tonight it's about a factory and building it. So tell me a little bit about the journey in the last 6 months, and how are you feeling?
Oh my gosh, it's been amazing the last 6 months. When we moved here in this facility, it was empty. There was nothing here. And then I asked the team, hey guys, we have to build our first full-scale prototype, but it's not just that. We have to build an entire factory that would make that prototype. And the team is like, well, can we achieve this? How much time do we have? And I said, 6 months.
I just said not enough.
and the team is like, I don't think it's going to happen. I said, it will, because you guys are the best. We'll make it happen. And so since then, the team had, not only worked on the design of the reactor, but also simultaneously working on the factory design. So we're thinking like, okay, you know what, we've got a design here. What kind of equipment do we need? What kind of layout should we have to optimize this? What is the production level we need to target for making not just the first reactor, but many, many, many reactors? So this is our pilot line, and we have not vertically integrated everything, but we have vertically integrated many things in this reactor. So majority of the stuff that we are about to show you tonight is something that we have built ourselves internally. So our team has been not only like setting up the factory, but actually building and welding and putting components together and finally finished a product that we want to put sodium in the next few months and load it up and actually do a full-scale prototype. And I think that's going to take us next level of our technology maturation.
Okay. Well, I think it's amazing just 6 months to go from an empty warehouse to what you've got already. And I know that it's not without a lot of effort. And you were just mentioning that. Have you learned anything along the way that you didn't know that you wish you had known when you started?
Oh, there's a lot. I think we learned quite a bit about how to make reactor vessels internally.
Okay.
That was one thing we thought was not possible by us, but we figured out a way how to make it. The other thing that I would say, which I think very important, our team originally said, okay, you know what? Let's focus on things that we can be good at and outsource the rest. And we want to outsource because they are metal fabricators. They make metallic parts all the time. But after this experience, we realized it's good to rely on vendors for onesie, twosie, but not for more than that. In fact, we have, there's a significant amount of lag in how the vendors would go, and the type of quality that we need, they're not up to par to those quality. So after this experience, we're like, you know what? Yes, we need to rely on our vendors, but for parts that are like pumps or compressors or any equipment that we can just buy that we don't want to get into, like turbines, for example. But everything that is metallic in nature, we need to build ourselves because nobody will build it faster, better, cheaper than us.
Not only that, but when you build it, you're your priority.
Exactly.
If somebody else builds it, what priority are you?
Yeah, I mean, the cost may be a slight delta, but I mean, we can live with that, but the timing, nobody can work at the sense of urgency that we want to move at.
Right.
We want to move extremely, extremely fast, not just in our development of the reactor maturity or the factory maturity, but about when we start production, we want to roll through and produce these reactors at a very fast turnaround.
Right. This is not just unique to you and making nuclear reactors. I've been listening to and we've seen some interviews with a bunch of people in the space industry, like say Vast Industries, who's making a space station. They said almost exactly what you just said.
Yeah. So. There is surprisingly a lot of correlation between rocket manufacturing and reactor vessel manufacturing. And again, I think one of the key things that we were able to achieve with this design is traditional nuclear, you need specialized equipment, specialized processes to make them. But what we were able to do is come up with a design where we can use conventional equipment like CNC mill, lathe, water jet, tank rollers, robotic MIG welders, things that we can actually buy that is used in other industries. We can just acquire and use it for our reactors. We don't have any equipment that is, manipulating or cutting metal that is unique.
Right. I was asking Matt about that. Anything that you have to make that is just for Aalo becomes extremely expensive.
Absolutely, absolutely. The most we have done is we've figured out how to load all the reactor internal components horizontally without needing a vertical crane because we don't have the headspace here, and it gets very challenging to pick up a very heavy thing and drop it down. So we figured out a way how to customize a jig to load all our parts horizontally without scraping or damaging the reactor vessel. Okay. I think that's something that we have put a lot of energy and time to figure out how to do that.
Well, that's awesome. Well, I know you have a lot more going on here today, but I just wanted to say congratulations. From just 6 months. It's amazing to me what you've done, and I'm really looking forward to what you're going to do in the next 6 months.
Yeah, so our plan is, today would mark the completion of a milestone, which is, can we build a reactor in a factory? And the answer is yes. So for the next 6 months, we're going to try to implement all our nuclear quality assurance in this factory so that when we build reactors, whether it be NRC or DOE authorization, both regulators will accept that as a nuclear reactor. So we're going to bring both of the organizations later this year to audit us, to do inspections on us, to make sure we are implementing NQA1 the way the regulators expect us to.
Awesome. Well, I hope to come back and see that in 6 months and hear how successful you are.
Amazing.
Thank you very much.